Welcome. Here is one great problem, and I invite all of you to solve it together. The problem is, let's conduct experiments with conducting balls. There are balls. During each experiment, we slowly bring together three solitary balls. That means isolated balls of radius r each, so that in the final state the centers of these balls are at the vertices of an equilateral triangle with side 3r. And write down in the laboratory journal the values of the work that we do. In this case, the balls in the initial state can be both charged and uncharged. Okay. In the cases shown in this figure AB, figure AB, the recorded values of works are A1 and A2. That means in this case A1 and in this case A2 work has been done by the external agent. Finding the potential of the charged ball in case A, that means this charged ball, and the potential of the both charged balls in case B, and the magnitude of work in case C. Okay, so it's the problem, and we need to consider the electrostatic energy of the system when it was formed. In fact, in the initial state, when the balls were all apart at infinite distance and only one ball was charged, and I know that in the initial state, the total energy of the system of conductors in the initial state, it can be written as half q kq by r, the potential at its surface, kq by r. I guess you know the formula, and so you can write it like half kq square by r. This is the basic formula. When the electrostatic energy is stored in this charged ball, it was only charged ball of the system and its radius being r, so its electrostatic energy must be this. And now, when the system is made like this, when the balls were brought together, then you can simply say that the potential of this ball, the surface, since other uncharged balls has come close to the charged ball, so the potential at the surfaces of each ball must have changed. Suppose that this potential energy is simply phi1, then both of them will have same potential energy phi2, because one symmetry is also available here. If we can draw a perpendicular and rotate it by 90 degree, nothing will change, so that means they will have the same potential by symmetry. And then you can write the final electrostatic energy of the system as U2, and that will be like again half, and Q phi1 is the energy of this charged ball, and because this other two balls haven't any charge, they hasn't got any charge, so you can write it 0 multiplied by their potential phi2 plus 0 multiplied by potential phi2, and that is simply half q phi1. This is the total energy of the system after the balls has brought together to complete the triangle. And now you can use the law of conservation of energy, and that is initial energy of the system plus work done, and the value of work done is A1 in this case, and this will become equal to U2, or call it U1 because we have many other systems to deal with, so just call it U1, and that is equal to U1. And you can write both of them as U0 was equal to half k q square by 2 plus A1 equal to half q phi 1 is the energy after they have been brought together, and you will get the value of the potential energy of the charge ball after they got together, and that will be simply, if we divide both sides by half q, we can get the result, and phi 1 will be k q by r plus 2a1 by q. So this is the energy in the first case. Now consider case B, and case B is something like this. Case B, this is the case B. We have two isolated charged capacitors, charged spheres, in fact, charged balls, and so we, in the similar manner, we can write the initial energy, electrostatic energy of the system as half q, and potential at the surface of one of the balls having charge q, and plus half is there, minus q was the charge on the other ball, and at its surface the potential was simply minus kq by r, and this, I think, is the initial electrostatic energy of the system. And if you can solve it, what is it? This is simply kq square by r, 2 gone because 2 they were added both, and so this was the initial electrostatic potential energy. Now when they brought together to form this system, you can see here one thing: the potential energy of this uncharged ball is equal to 0, because it lies on an equipotential surface, because the potential due to this at here and potential due to minus q at its position are equal and opposite in sign, equal in magnitude and opposite in sign. So the potential of the uncharged ball is equal to 0. You can see right like that this point is O and this point is O dash, then you can say that there is an equipotential surface containing the plane O dash, containing the plane that contains the line O dash. And I would like to write in this case that phi 1, phi 2 I included in this case. So I'm going to write, when they brought together, its potential simply becomes phi 3, and that means its potential is going to be minus phi 3, and its potential is equal to 0. So now I can write the potential energy, total potential energy of the system after they got together, and what will be the potential energy in this case? This is this you can write as U2, and this U2 you should like to write for q phi 3, half q phi 3 is the potential energy of the left side of the ball, this ball, and it has got a potential energy minus q multiplied by minus pi 3, and third one has 0. So you can write the total potential energy as half q phi 3 plus minus q minus phi 3. You don't need to write anything else, as you have changed the potential energy at its surface, and due to mutual interaction, its potential energy has changed to phi 3 and minus phi 3, and so both summed up, and you get the value that final potential energy of the system becomes phi q3, and you can use again the law of conservation of energy, and you can write that initial potential energy, initial electrostatic energy plus work done in this case was A2. So initial potential energy plus work done by the external agent equal to U2. And you get from here what the value of phi 3 you needed to find out. And phi 3 was K, phi 3 you can get KQ by R plus A2 by Q. And this was the potential in the second case. Now in the third case, that is a special case, in which we have this system, and we need to find the magnitude of work in this case. So one thing is evident here, if I can think that in this case we have balls situated like this, and ball was charged like it had charge plus q, it had charge plus q, and it had charge plus q. And you need to visualize like this, that look, I have to remove something first, and I can write it like this: plus q plus q plus q, where the charges before brought them together to form the equilateral triangle. So initially they were all separated at infinite distances from each other. That means they were isolated from each other. So I can write the initial potential and initial potential or initial electrostatic energy simply as U naught is equal to half, and all three charges 3q, and at each of the surfaces the potential in the electric potential was kq by r. So this, I think, 3 by 2 k q square by r is the initial electrostatic energy of the system in when they were isolated, and when they brought together their potentials, you can see, has become something, I don't know, whatever it is, but it will be something same potential energy to all of them. And if you can consider the problems you have solved already, that means part 1 and part 2 of the problem, you might consider that this system plus q and plus q is equivalent to this thing, plus q nothing here, and plus q here, and or plus q here, and plus q. The system is equivalent to this system. The given in the problem is equivalent to this. Superposition of all three is the system on the extreme left. And we know in this case, its potential we observed was phi 1 in the first case, and their potentials were phi 2, phi 2 simply. And we can do the same thing in here. We can say that the potential of the ball here must be phi 1, and these two will be phi 2 and phi 2. And same case here, so that the system is equivalent to, the system given in the problem is equivalent to, I think I would, perhaps I'm trying to say that the problem is a superposition of three distributions. And perhaps if you know the uniqueness theorem, you can say, according to the uniqueness theorem, there cannot be other distribution. So that means we have this distribution like this. And in each case, you will find that the potential at this position is phi 2 plus phi 1 plus phi 2. That means potential here is phi 1 plus 2 phi 2. And in this case also, potential is phi 2 plus phi 2 plus phi 1. That is phi 1 plus 2 phi 2. That means our phi 4 is simply phi 1 plus 2 phi 2. And here you can see q1 plus q2 plus q2, that is q1 plus 2q2. So if we can find the value of q2, we can get the result. But the problem is, how can we find the value of q2? Phi 2, sorry, not q2, phi 2. And to solve this puzzle, I'm going to draw another picture. And I knew in the second case, case 2, here was charge plus q, here was charge minus q, and here was nothing. And its potential was equal to 0, and its potential, perhaps I wrote down its potential as phi 3, and its potential is minus phi 3. If you can try to make a superposition, this will be the superposition of two systems like this. Its potential, if this is going to be the sum of these two, then its potential must be phi 2 and its potential must be minus phi 2. And if I put a charge, this potential is phi 2, and if I place, no, this is an basically nothing is here, no charge is here. But if I can put the charge plus q here and charge minus q here, its potential is going to be minus phi 2, minus phi 1, because its potential I'm going to write phi 1. And we had this situation earlier in the problem, in the part 1 of the problem. And this potential will become simply as minus pi 2. You can see the similarity between them. If I can put a charge q here, this potential is going to be phi 1, and these two positions are empty positions. Empty, that means there are no charges there, so their potential will become phi 2 each. And if I put the same thing here, charge minus q1, I can take its potential as minus phi 1, so these two positions will have potential minus phi 2. So they are all in agreement. And you can see that this is in combination, the superposition of these two configurations is equivalent or equal to this configuration of charges. And if you compare them, you can write simply equation here as phi 3. If you want to calculate phi 3, I'm not calculating phi 3, I can simply comparing them. This phi 3 can be written as phi 1 minus phi 2. Phi 1 minus phi 2, this phi 3. And phi 2, if you write to get phi 2, because we are looking for phi 2, we can compare the potential at this position, and you can write minus phi 3 will be equal to phi 2 minus phi 1, and in that case you will get phi 2 equals phi 1 minus phi 3, and we already have the values of phi 1 and phi 3, and let's see what were the values of phi 1 and phi 3. Phi 3 is here, and phi 1 is here. So if you can put these values, the phi 1 is kq by r 2a1 by q, and this is kq by r plus a2 by q. So I can write here the respective values, and I can get the result as kq by r plus 2a1 by q was phi 1, and phi 3 was kq by r plus a2 by q, and just we can solve it, and we can get finally that phi 2 is equal to 2a1 minus a2 upon q. So we got the value of phi 2. Now we need to find the value of work in this case, and the initial energy of this system when they were all isolated, it was u naught, and we can write it half. All the three charges has same values, so I can write it 3k and k q by r, so that the initial electrostatic energy of the system I can write 3 by 2 k q square by r. That's right. And now the final energy of the system. Writing final energy of the system is Eg, because they all have charges there and their potentials, and they all have same charges and same potentials. So the final energy of the system is going to be half 1 by half 2, that is half 3 times of q phi 1 plus 2 phi 2. So this is I guess is the final electrostatic energy of the system, and you can write the values of now phi 1 and phi 2, and you can get 3 by 2 q you can take out, and you can write phi 1 was k q by r plus 2a1 by q, and phi 2 phi 2 was 2 phi 2, I just got 2a1 minus a2 by q, that is 2a1 minus a2 by q, and you can solve them. I can also solve it, and what I can get from here, 3 by 2q k q by r plus 6a1 minus 2a2 by q, and from the law of conservation of energy we can write here u naught plus work done a3, in this case it was required, equal to u3, and we can get the value of a3 by simply subtracting u naught from u3, and the result I guess you can get is 9a1 minus 3a2. So This is the final solution or the solution of part 3. Thank you very much for watching.